In this video, we're going to take a look for Physical Science 102, Physical Science Survey, second semester. We're going to take a look at Chapter 13, Chemical Reactions. This covers a lot of ground, so I may have to move through it rather quickly to get done in a reasonable amount of time. So what you'll want to do is watch through a section, maybe pause it, and maybe even go back and look at the section again. Okay, so first thing I'm going to do is share the PowerPoints. And the PowerPoints are in Brightspace, so you can access those independent of this video if you wish. Let's see. One other thing before we get rolling here. What I want to do is lock the meeting so we don't get interrupted. All right, now we're going to share. Okay. Let's see. Slideshow, there we go. Okay. Just a little bit bigger on my end so I can see what I'm doing. Okay, chemical reactions, chapter 13. When we speak of properties of a substance, we're talking about those things that identify the substance as unique. In other words, they distinguish it from any other substance. These are properties. Some of those properties may be physical in nature. And the best way to describe physical properties are those, in fact, properties are, it's often convenient to think of properties as the potential for a substance. What does it have the potential to do? In some cases, when we talk about physical properties, we mean those characteristics that identify the substance without referencing any type of possible change in the substance. In other words, if that property changes in any way, it doesn't change the identity of the substance. For instance, density. Density is an expression of the mass of something per unit volume. Okay, that's density. It may be expressed in terms of, and very often, in terms of grams per cubic centimeter. That's typical for solids. Or grams per milliliter, which is typical for liquids. Now you can express those either way, and the number that accompanies those units will be exactly the same. The reason being that a cubic centimeter and a milliliter are identical. They're just different ways of expressing the same thing. Okay, so density is a physical property. Density implies no actual change of the substance. For example, if we have a liquid, and we say the liquid, for water, for instance, let's say water, we say that water is 1 gram per milliliter. If we heat water, then it will occupy more volume. Volume will increase, right? So the denominator increases. That means the quotient of the two, because the mass won't change, the volume will change, So the density will decrease, but it's still water. That we haven't changed the water at all. So it might drop down to maybe 9985 if we heat it up enough. Okay, other things that are considered physical properties are like hardness. And we can say something is very hard or very soft. That's a qualitative expression. Or we can assign a quantitative, a value to it. And there are a number of different scales that can be used to describe hardness. One of the most common, and one that's typically used for describing this physical property of minerals, is the Mohs scale. And it's based upon a series of minerals that have a fixed hardness in the scale. And all you have to do is take your unknown mineral and compare it to the other in terms of, does it leave a mark on a scratch plate? Or will it scratch? Will one scratch the other? And you can tell if it's harder or softer. And the hardest one, Mohs 10, is diamond. The hardest naturally occurring substance. We may mention that again when we get to the next chapter on organic chemistry. Because diamond is made of carbon. Or the softest in this scale is talc. Very soft mineral. Okay, that's hardness. What do we mean by phase? Well, put it simply, phase is either solid, liquid, or gas. And we know how to characterize each one of those. Color can be a physical property. Melting point, right? Pure water melts at 0 degrees Celsius. Electrical conductivity. Is the substance a good conductor or a poor conductor of electricity? Specific heat is another one that takes a little more explaining, and probably at this point I should let you look that one up for yourself because I'm already getting long-winded. All right, chemical properties. What's the difference between physical and chemical properties? Chemical properties describe a substance in terms of its potential to transform into a different substance with a completely different identity. Whereas physical properties describe the potential to change, but not change the identity. Okay, so what do we mean by that? Well, a good example would be if we say this substance is flammable. It has the potential to burst into flames under certain conditions. Or this substance will rust if it gets wet in an oxygen atmosphere. Or this substance has the potential to decompose. If you heat it, then rather than change phase or expand volume, it will actually break down into different substances, decomposition. Okay, those are examples of physical and chemical properties and the differences between the two. Let's see, this is repetitive, so I'm not going to stop here. Now, when we talk about those are properties, they describe the potential relative to the substance identity. A change actually describes the process itself based upon that property. So when we say water melts at 0 degrees centigrade, we're saying that it changes from the physical state of solid to liquid. Well, actually, that's what happens. we've described that we are melting ice into water. That's a physical change. Similarly, chemical change. If we say we light the burner on the gas stove in the house, we're going to cook a meal. Then when we do that, we are the description of the gas that comes out of the stove, we could say has a chemical property of flammability. But it actually doesn't do that until you turn it on and spark it or light it with a match. In that case, it undergoes a chemical change. Chemical change from natural gas, which is predominantly methane, and combining with oxygen produces carbon dioxide and water. That's a chemical change. And the way we describe that change is in a form of notation called chemical reaction. So this, we can describe it in words, the chemical reaction. For our example here, decomposition of water into hydrogen and oxygen gases. And you can do that. All you need is water. Need to maybe add a little bit of acid to make it conductive so electricity will flow. And then you need a direct current. And if you pass a direct current through water, the energy from that electrical transfer will cause water to decompose. And we would write that, we could describe it here, or we could write it in terms of a chemical reaction, which I'll describe in just a few minutes. Now, what happens during this chemical reaction? Well, I think we've described at some point in the past, I believe I gave it in some detail in the previous video on chapters 11 and 12. That during a chemical reaction, no mass is created, no mass is destroyed. You got the same mass before as the mass afterwards. And that's a consequence of the law of conservation of mass proposed by Antoine Lavoisier, and has since been proven. And then that was just the law. Dalton's atomic theory actually explained why that is. And the reason you have the same mass before and after is because you have the same atoms before and after. The only thing that's happened during a chemical reaction is just they rearranged, changed partners, or separated from their partners, as would be the case with the decomposition of water into hydrogen and oxygen. So that rearrangement of atoms explains the nature of a chemical reaction. And you produce different substances, new substances during a chemical reaction. This is the artist's idea of what happens if we take that hydrogen and oxygen that we just separated and put them back together, put them in a vessel and spark them, give just a little bit of bump of energy, and they will react and produce water again. So what that says is the reaction can go either way. Either you can decompose or you can synthesize. Okay, so when we write this chemical reaction, there are conventions that are agreed upon by scientists everywhere. And let's use our example of, let's use methane combustion that I described earlier. So methane is written like this. That compound, 1 carbon, 4 hydrogens together in a single molecule, combined with oxygen gas, and notice that oxygen is diatomic. It's one of those diatomic elements. Hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, iodine. They're all diatomic elements. under conditions of 1 atmosphere pressure and room temperature, 25 degrees Celsius is the standard. All those elements will be diatomic. So when we combine this with that, right, if we light that burner, where does the oxygen come from? Well, from the air, right? Oxygen's in the air. There are other things in the air, but oxygen is the one it wants. And then these are the reactants. And when they react, they form products. And the products they form are carbon dioxide and water. Okay? So we say methane plus water yields carbon dioxide and water. Now, another thing that we do when we write these equations, sometimes it's important, in fact, sometimes it's essential that we know what their phase is. So in this case, the phase would be gas. In this case, the phase would be gas. And this one's a gas. If we allow this one to condense, it will become a liquid at room temperature, but in the flame itself, it's still a gas. Right? So we designate gases with a G, liquids with an L, solids with an S. And then if we have the reaction is going on in aqueous solution, in water, dissolved in water, then we use an AQ right here. That AQ means aqueous, in water solution. Sometimes there are extra bits of information that we want to include in the reaction. For instance, if there is a catalyst involved, we would put it here over the yield sign. That means the catalyst is intermediate between the two. It is facilitating the reaction. Or if we want to show that the reaction can go forward or reverse, then we may, instead of using that single arrow, we might use a double barbed arrow to say it can go backwards, forwards, or backwards. Okay, this is just a rehash, but it contains little bits of new information. We know that during a reaction, these reactions tend to disappear or they decrease. There may be some of this left over, right? If you stop the reaction before it's completed, then you might have some of this left over and some of that in addition. So you may have a mixture of all four of them. New substances are formed in a chemical reaction. That's a given. And then there's the issue of energy, right? The reason we're combusting this methane is so we can get energy from it. So in this case, heat is evolved. So sometimes if that happens, then we'll use a symbol like this. That stands for heat. Now, sometimes that symbol stands for we add heat to make the reaction go, and sometimes it's heat's evolved. In fact, that could be ambiguous. We don't know whether we've added the heat or the heat came out of the reaction. So very often what we do is if the heat comes out of the reaction, we'll put it on the reactant side, right? And we'll say plus heat. But if we have to put heat in, or heat is absorbed during the reaction, we'll put heat on this side. So in that case, heat goes into the reaction and it absorbs heat in the process. And here it gives up heat. Sometimes during a reaction, we don't just get heat, or heat's not involved. Sometimes there's light. Like when you light a candle, right? The whole purpose of lighting a candle is to produce light. And that's energy derived from the reaction. Some reactions produce electricity directly. In hydrogen fuel cells, they act like batteries, but they're really chemical reactions that are going on. Well, batteries are too, but a fuel cell is a special type of battery. And they produce electricity directly from the reaction. Sometimes a reaction, when it's produced, will generate sound. When fireworks are shot up into the air and they explode, they produce sound. That's a release of energy. Okay. A chemical reaction can be written, an equation, a chemical equation can be written for any reaction. Can be. Sometimes it's difficult to tell what the products are and what the reactants were in very complex situations. But sometimes you can even predict what the reactants, what the products will be. Most of the time you have to be told, and then you deal with it from there. What we also need to do is when you write a chemical reaction, an equation, you have to know and write correctly what are the reactants, right? This one has to be CH4, that's methane. If you write it any other way, then it's going to affect the outcome. It may not even happen. So we have to be sure that these are written correctly. CH4, oxygen diatomic, carbon dioxide, yep, and water. So those are written correctly. Then we're faced with a situation, if we're going to have an equation that has the same mass on both sides, we have to have exactly the same number of each of the atoms on both sides. Notice, here's one carbon reactant. There's one carbon, right? That's good. Here, 4 hydrogens. There are only 2 hydrogens here, right? So this equation is not balanced for the number of atoms of each element. Oxygen, there are 2 oxygens, and here there are 3 oxygens. So we need to balance the equation. We need to make adjustments so that we have the same number of each element on both sides. Now, one rule that cannot be broken. Once you have written the reactants and products correctly, you cannot change those formulas. They must be untouchable. So the only way that you can balance now is to use prefixes. We call them coefficients. So you change the coefficients in front, and that changes the number of each one. So if we put a 2 in front of the CH4, that means we're saying there are 2 molecules of methane, which also means there are 2 carbon atoms and 8 hydrogens. Okay, coefficients multiply by everything in the molecule. So that's how we balance an equation. Now I'm going to show you how to do that in just a minute. By the way, the lab exercise that goes with this process, balancing equations, takes you through steps to try to emphasize the fact that you need to have the same number on both sides. But it doesn't give you the most efficient way to balance an equation, right? So the way you complete the lab is slightly different and more involved than the way I'm going to give you to balance these equations. So we need to look at how to balance equations. That's essential before we can do anything in chemistry. We need to be able to describe the reaction completely, and that means a balanced chemical equation. Now, these are the steps that are given by the authors of your textbook. And they're not wrong. It's just they really don't give you enough information to do the process reliably. Balancing chemical equations is a skill like any other, requires practice and requires lots of different examples that have to be dealt with, have to be mastered. And then the more of them you do, the easier it gets to see patterns. So first and foremost, an equal number of atoms of each kind must be represented on each side of the yield sign. And you do that with coefficients. Which brings us to the second rule. You cannot change the formulas. Once those formulas are written correctly, you cannot change them to balance an equation. And then if you have coefficients and you've established that you have the same number of each element on each side, then you need to look at the coefficients and see, can they be reduced? Can you divide them by a whole number and reduce that value? The final set of coefficients of the equation should be the smallest whole number ratios possible. All right. So what I've developed, and you'll notice a change in the slide here. I brought these next two slides over from my chemistry course. And I think let me just, before we go into these hints, let's balance this equation. Okay, using my budget method. All right. So in order to balance the equation, you don't necessarily need the phases. Sometimes you do, it helps. But in this case, we're going to do away with the phases because they take up room. All right. So we'll get rid of this part. Here we go. And when you write the unbalanced equation, you need to leave room in front of each of the compounds and elements, as the case may be, to put numbers in there. So I need to rewrite this. Let's do it this way. Say, like here, 4 plus O2, leave some room in there. And then CO2, and then water. Okay. Now, be sure I get everything still on screen. I mentioned budget method. Okay. What you want to do is find out exactly where you're starting. And what I mean by that is, how many elements are you starting with on each side? So in order to do that, I list down the left-hand side the elements that are contained in the equation. So carbon's there, hydrogen's there, oxygen's there. That's all of them. Carbon, hydrogen, oxygen. It counts for every element in the equation. And then on this side, you count up the number of each one and just write it down. So there's 1 carbon, there are 4 hydrogens, and there are 2 oxygens. And on this side, there's 1 carbon, 2 hydrogens, and 3 oxygens. Okay. Now, once you have, this is your starting point. The next question is, where do you start to balance? Where do you go in here? Well, that's part of these helpful hints that I've put together for my chemistry classes. If an element, the first hint is, if one of the elements appears by itself, in other words, it is an element in the reaction, then leave that one alone until the last. The reason being, if you put a coefficient in front of that, that's all, it only changes that element. If you put a coefficient in front of that, it changes carbon and oxygen, which means that you have to respond by checking the other side for the other element. So leave this one to last. And we usually try to leave water to last too. Okay. Now, don't worry about that hint number 4 yet. Okay, so where do we start? Well, it doesn't do any good to start with carbon because it's already balanced. Now, that situation may change, but right now we don't start there. How about hydrogen? Hydrogen occurs in one place here and in one place there. Okay, that would be a tempting place to start. And if we did start there, we could still end up balancing the equation, but we're trying to be most efficient and take the fewest steps. So very often when you have a situation where there's even, it's easy to balance those. But where you have an even odd, that may be difficult. So we look and say, okay, what do we have here? Well, we've got 3 oxygens, but if we put a 2 in front of that, and this breaks my other rule, we're going to do water before we do anything else. So it's not hard and fast. If we put a 2 in front of that, that makes that one even. Okay, so let's try that. If we put a 2 here, my marker works. No, it's not going to work. If we put a 2 here, that means we have 4 hydrogens. Notice I crossed out the old one and put the new one in. 4 hydrogens total. And then we also have 4 oxygens. Okay. Now where do we go? Well, carbon's balanced, hydrogen's balanced. How about oxygen? We left oxygen till last. So if we've got 4 on this side and 2 on that side, if we put a 2 in front of that one, that'll give us 4 oxygens and we're done. Okay, that's the beauty. One of the nice things about this budget method, you can see as you proceed, you can see when everything's balanced because the numbers match on both sides. You don't have to constantly go in and recalculate. So that was balanced. And if we look at the coefficients, we can't reduce them any further because that's a 1. You can't make 1 any smaller. Okay, so that's the method in general that we use to balance equations. What I've got on this slide is a combustion reaction where we have this compound and reacted with oxygen to make carbon dioxide and water. Okay. So how do you balance that one? Well, I didn't show you. Let's see. No, not yet. This balancing relates to the 4th hint. It's true that we want to end up with whole number coefficients. Simplest ratio of whole number coefficients for the balanced equation. But on the way to that end game, it may be convenient to use fractional coefficients. That's what I've done here. Now, this doesn't show you how we got there. So let me take a different one. like, let's do, this is octane, C8H18 is octane. That's the stuff you burn in your gas tank. Let me do hexane. There we go. Hexane. It's another hydrocarbon. And we're going to burn it in oxygen. And it makes carbon dioxide and water. Okay, we need a budget. So we're going to have carbon, hydrogen, oxygen, 6 carbons on this side, 1 carbon on that side, 14 hydrogens on this side, 2 hydrogens on that side, 2 oxygens on this side, and 3 on that side. Okay. Now, we could start with the same way we did before and put a 2 over here. But I try to avoid that unless I have to. And I had to in the past one. That was because the carbons were already balanced. But if we balance the carbons first, then that means we need a 6 here. Right? That means 6 carbons. And now we have 12 and 13. So we have 13 oxygens. Now on this side. Okay, how about hydrogens? Well, we've got 14 hydrogens here, and we only have 2 on that side. So if we multiply that one by 7, that will give us 14 hydrogens. We're good there. But it also gives us a change in oxygens. 12 plus 7 is 19. Okay. Now we've got the carbon and the hydrogens balanced, but we don't have the oxygens balanced. We need 19 oxygens on this side. So how do you get 19, which is a prime number, out of a 2? Not easily, but the trick is use a fraction, right? If we use a fraction like that, then 19 halves times 2 is 19, right? The simple math. 19 halves times 2, 2's cancel, and you got 19. Okay, so that will give us 19 oxygens. But we don't have whole numbers as our coefficients. So how do you get rid of the fraction? Well, we can multiply that whole equation through by the same number, right? It's kind of like math that way. If you do the same thing to both sides of an equation, then you haven't changed it, right? If you add something on this side, you add something on that side. If you multiply something times this side, you multiply the same times that side, and the equation is still the same, mathematically speaking. Well, we can do that in chemistry too. So if we multiply this whole thing through by 2, right? Now we get 2 here. We cancel the 2 here, right? 19 halves times 2. 2 times this is 12. And 2 times 7 is 14. So the balanced equation now, it was balanced before. Right? That's still true. But now it would be 12 and 12, 28 and 28, 36 and 36. 38 and 38. Okay, so now that one's gone. So our balanced equation is 2 hexane plus 19 oxygen molecules yields 12 carbon dioxide plus 14 water. That's balanced. And you can check it. There's no way to reduce this one any further because 19 is a prime number. You can't divide anything into it. Okay, so that's the next to the last trick. Use a fraction if necessary to balance your equation and then get rid of the fraction in a subsequent step. All right. Okay. Now, number 5 is just simplify the equation. The last hint, if, let's see, I'm not sure if I mentioned earlier, I think I did, polyatomic ions. Yeah, I'm positive I did. Polyatomic ions, as a reminder, are ions that have a charge, obviously, but there's more than one atom in the group. They're bound together in such a way that they share, and the charge is assigned to the entire group. It doesn't reside on any one atom. It's over the whole group. So for polyatomic ions, if you have polyatomics on both sides of your chemical equation, and they have not been broken up or changed in any way from one side to the other, then you can use them as a balancing group. In this case, you see we've got ammonia on this side, right? Nitrogen, hydrogen, ammonia on this side, and that's it. That's the only place it occurs. Same thing with phosphate, both sides, unchanged. So what I've done here to set up the table is, these are your balancing groups or elements: ammonia, phosphate, calcium, chlorine. And in this reaction, right, this one is ammonium phosphate. Notice that the phosphate has a 3- charge, and ammonia only has a 1+ charge. So we need 3 positives to balance the 3 negatives, right? So that one is written correctly. That's the first rule. Your compounds must be written correctly. So now we can do our initial budget tally. All right, so we've got 3 ammonias on this side, got 1 phosphate, 1 calcium, 2 chlorines. And on the other side, we have 1 ammonia and 2 phosphates and 3 calciums and 1 chlorine. Now, where do we start? Well, sometimes it's sort of like intuition. If you do enough of these, then you figure, where should I start? Well, none of them are equal at this point. So just start someplace. I think I started with calcium. Yeah, I started with calcium. So we put a 3 there, and there are no single elements in here. So we can't use that reserve the single elements till last, because they don't exist. So if we put a 3 in front of there, that gives us, right, 3 calciums for the reactant side and 3 calciums for the product side. Now what we've done is we've changed the chlorines, right? The chlorines now, instead of 2, are 3 times 2 is 6. All right. So now we're going to change in such a way to balance the chlorines. We need 6 chlorines on the product side, right? And that also changes the number of ammonias. We have 6 ammonias and we have 6 chlorines. Okay, is anything balancing yet? Well, the chlorines are balanced and the calciums seem to be balanced. So what's next? Well, let's balance the phosphates. Right? We got 2 phosphates on the product side, so we need 2 phosphates on the reactant side. Okay, And that changes the ammonias. So now we have 6 ammonias and 2 phosphates. There we go. And you can tell from just looking at it, let's see, did I fill in any more? Yeah, I just filled them in. That we're balanced. 6, 6, 2, 2, 3, 3, 6, 6. Everything's balanced. All right. So now we're back to, now we're back to the original slide set. Okay, this is just an example. Right? If we have an unbalanced equation, this one is simple. I mean, we don't even have to set up a budget, really, because if we put a 2 in front of the hydrogen iodide, we get 2 hydrogens, 2 iodines on the reactant side, and we've already got 2 hydrogens, 2 iodides on the product side. So that's balanced. And it's the simplest whole number. Okay, these are some other tips. Let me see if they're any different from the ones I've already given you. Right, you got to count the atoms or groups, as the case may be. Sometimes reactants occur where the polyatomic is busted apart. In that case, you got to go to individual elements, individual atoms, and balance that way. They tell you to start with balancing an element that's present in only one place on both sides of the reaction. Okay, I'll do that. Let's see. Here's your fractional. Okay, so they also advise to use fractions when necessary. And then once the equation's balanced, get rid of the fraction. Here's another example. Let's see. There's nothing new there, so let's move on. Okay. How about this one? Sodium azide. That's what N3 is, azide. It's a polyatomic ion. Sodium azide. Azides are used in I forget the name. Crash bags, in your cars. When you crash your car, within a millisecond, a spark goes into that bag and causes the decomposition of sodium azide to sodium metal and nitrogen gas, and it expands at an unbelievable rate. It just like that. That's why if you've got a small child on one side, or a pet, and that thing actually accidentally goes off, it can kill the person sitting in that seat. So this reaction takes place when the bag goes off. So we've got sodium azide, and it produces sodium plus nitrogen gas. All right. So if we use our budget method, we need sodium and nitrogen. That's it. 1 sodium, 3 nitrogens, and 2 nitrogens. So, 1, 2. There we go. Okay, what do you do when you've got an odd and an even? This is not always the case, but sometimes it's valuable to use a mathematical technique called cross multiplication. So if we put that 3 over here and this 2 over here, what will happen? Right? This is already balanced. So if we put a 3 over here and a 2 over here, that makes 6 nitrogens and 6 nitrogens. Okay. And now sodium is off by itself. We saved that one till last. So now we have 2 sodium. 2, 2. And oh, this one's also 2. Forgot to change that one. So now we're balanced. So that's a technique that I didn't, a hint that I did not include in that slide set. And it should be there. I must have used an earlier one. Because cross multiplication can be useful at times. Airbags. There it is right there. If I read my own slides, I'd know what it says. In car airbags. They're not actually air, they're nitrogen bags. Okay. Now, there are different types of reactions, and sometimes it's helpful to recognize what type of reaction we're dealing with. This is called a combination reaction, or sometimes it's referred to as a synthesis. You'll see it both ways. A combination reaction is a synthesis in which 2 or more elements combine together into a compound. Just the opposite, go the other direction, is a decomposition. You take a compound and break it into elements, that's a decomposition. We showed you one earlier with water. We decomposed water into hydrogen and oxygen. And in the next slide, we did a synthesis where we had oxygen, hydrogen combining to make water. Now that reaction itself is extremely energetic, lots of energy. That's why they used it in the main engines of the space shuttle. Liquid oxygen, liquid hydrogen in that big orange tank. You go back and look at Google Space Shuttle. You'll see that big orange tank on the belly of the space shuttle. It contains both liquid oxygen and liquid hydrogen, and they're combined in the 3 main engines of the space shuttle to make water and lots of energy. That, in combination with the solid rocket boosters, gets that thing into the, well, used to get that thing into orbit. They've since been retired. Okay. During a chemical reaction, remember, we're rearranging elements. So what does that actually mean at the molecular level? It means that bonds are breaking and being reformed in many cases. So when you break a bond, you've got to add energy. And then when you form the bond, you get energy back. So that balance determines whether the reaction overall is going to release energy or absorb energy. So if it takes, let's use a generic reaction. Say we have A combined with B and C with D, and then we're going to take C with B now and A with D. Okay, so the bond that holds A and B together had to be broken. So we had to add energy in. We had to add energy here. Okay, over here, we get energy back as these independent atoms now, after the bonds are broken, recombine in this form. And now we get energy back. Okay, the balance, did we put in more energy than we got back? Then things are getting colder, right? We're losing energy in the process. It's being stored in these bonds, actually. Or if we put in a little bit of energy and get a lot of energy back, then let me use the correct terms. If we put energy in and don't get much back, that's called endothermic. Okay? If we put a little bit of energy and get a lot back, like we're burning methane. And that's called exothermic. We get energy back. It gets hot. Okay, and that energy can manifest itself in a number of different ways. Light, heat, electricity, sound, whatever the case may be. Okay, so this exothermic reaction, when we are expressing it as exothermic, then we usually put the energy term on the product side, right? Energy was stored in these bonds. We broke them and reformed, but we didn't put all the energy back. We got some left over. So it's on the product side. That's an exothermic reaction. Energy is released. Okay, let's see. An endothermic reaction, we put energy in on this side and we don't get all of it back. Okay, now if we look at that in terms of a graph, this energy graph, right, we can say the reactants have a certain amount of energy, like on the y-axis. And then if we add some energy to it to make the reaction go, right, then when the products end up over on this side, they have less energy than the reactants did. Well, where'd that energy go? That's exothermic. It gave up that energy. Now, the energy we put in there to make the reaction go is called activation energy, right? They identify here as EACT, or E little a is good enough. And then the energy of the reaction is E sub R. Now you can do one of these graphs for the other one, the endothermic, and I think they will in the next slide. Yeah. In this case, we've got a certain amount of energy in these reactants. And then when the products form, the energy that we put in, this activation energy, we don't get all of it back. Okay. That's endothermic. Okay. So by definition, activation energy is the amount of energy necessary to make a reaction start, to get it going. Now, very often what happens is, once you get the reaction going, if it's exothermic, it gives up enough energy so that it provides its own activation energy as that excess, and that keeps the reaction going. It's self-sustaining. But for activation energy into an endothermic reaction, you've got to put energy in somehow from an external source. That's why when you have an endothermic reaction, usually you can feel it gets cold. Okay. Let's see. Oh. We can think of this activation energy in terms of kinetics. That is, this was a concept in the first semester, kinetic energy. Kinetic energy is energy of motion, if you recall. So there's a theory about chemical reactions called the kinetic molecular theory. And it just says that in order for a reaction to go, one of the conditions is you've got to have enough kinetic energy when these molecules collide to exceed the activation energy. That's not the only condition, but that's a major one. So this molecules have to collide. They got to come into contact or they won't react. So when we strike a match, we're providing the kinetic energy through friction. Now, how does heat flow in an endothermic versus an exothermic reaction? This is a concept that we cover in general chemistry under the topic of enthalpy, reaction enthalpy. And it helps to visualize the reaction in terms of system versus surroundings. So if you say the system is this, that's actually the reactants are in here. And everything else is surroundings. Then which way does the heat flow? Right? If heat flows during the reaction, if heat flows out of the system, that's an exothermic. If heat flows into the system, that's endothermic. Okay, it's just that simple. Whoops. Here we go. Now, I don't think we're going to be doing any calculations there. So there is a sign convention that you apply to the numbers if you do a calculation here. And I don't think we're going to get into that. No. Okay. But if you're ever confronted with this in terms of the numbers that are involved, energy units, then if it's exothermic, everything's in terms of the system. So if energy is leaving the system, the numbers associated with that energy leaving are negative. And if they're being added to the system, they're positive. Right? You won't need that for this course, but you may see it in the future, and I just don't want you to plead ignorance. Okay. What's the difference? How do we define an explosion? Well, an explosion is an exothermic reaction, but the key is how fast does it occur, right? Now we're talking about chemical kinetics, right? How fast does it occur? If it occurs almost instantaneously or over a very short period of time, we can call that an explosive reaction. Many combustion reactions can be made explosive if we confine them, right, into a vessel and they build up pressure and then they release that energy quickly. That's how the, I think the guy's names were Tsarnaev brothers, who bombed the Boston Marathon several years ago. They created a bomb out of gunpowder. They just put gunpowder into a pressure cooker. And when they set it off, it ignited, but not fast enough to be an explosion on its own. So they confined it in that pressure cooker. And when the pressure finally built up enough to exceed the limits of the cooker, then it exploded all at once. And they had shrapnel in there, right, to maximize lethality. And they eventually paid the ultimate price themselves. Okay, a combustion reaction. A combustion reaction is an exothermic reaction, but it always has oxygen. Something plus oxygen yields something else plus energy. So the key to a combustion reaction is that term right there, oxygen. I mentioned hydrocarbons earlier. When I balanced the equation with hexane, C6H14, that's a hydrocarbon. It's a hydrocarbon because it's got hydrogen and carbon in it. That's it. And when they burn, when they combust, they're always exothermic. And they give off carbon dioxide and water when they combust. Complete combustion gives you that. Now, there's such thing as incomplete combustion, and that occurs inside internal combustion engines, like the engine under the hood of your car. If you still have one, if you've got all electric, then you don't need to worry about this. But when that hydrocarbon combusts inside the cylinders of your car, the environment, if it's not perfect in chemical terms, then it will produce intermediate compounds, intermediate products that are not complete. They don't go all the way to carbon dioxide and water. And in fact, inside the engine, you don't have just oxygen, right? You've got air, and that's nitrogen. And under the conditions that occur inside the cylinder, you can convert nitrogen to various oxides that are pollutants, right? So that's why, at least in this country, cars are manufactured with catalytic converters in the exhaust stream. And what they do is they take those incomplete combustion products and, using a catalyst, and I'll explain what that is in a few minutes, they promote the further reaction to innocuous compounds. They complete the process. Unfortunately, the catalytic converter doesn't give you any benefit. In other words, the energy that's released in a catalytic converter is just waste heat. Okay, so this is characteristic of any of the hydrocarbons, carbon, hydrogen. Right? When you combust them with oxygen, complete combustion always gives carbon dioxide and water. So that's one of those reactions that you can write the products. You'll know that if it's a hydrocarbon and oxygen, you'll always get carbon dioxide and water as a product if it's a complete combustion. Okay. We can take time to balance these equations, but I'm already running really late, so let's move on. You get enough practice with these, with your homework and with lab exercise. Okay. Oh, well, here's an example of incomplete combustion. Right? For this heptane, it will produce carbon dioxide and water, but it'll also produce carbon and carbon monoxide. So carbon is typically referred to as soot, and carbon monoxide is just deadly, right? That's why people who want to commit suicide using an internal combustion engine in their garage, they just close the garage door and start the engine running and sit there until the carbon monoxide takes them out of this world. Not that anybody should do that. I'm not suggesting that. It's just that's what happens. Okay. Now, the balanced chemical equation describes before and after in a chemical reaction. But it doesn't say anything about how fast you get there. How fast does that reaction occur? There are various factors that go into answering that question. The four primary variables for how fast the reaction goes. One is temperature. If the temperature of the reactants is high, then you would expect to increase the rate of reaction. And that's based upon the activation energy. If you have more energy going into the reaction to start with, then you get more reactants producing products more quickly. Concentration. If you have reactant concentration increased, then according to that kinetic molecular theory, you have more chance to interact, right? They're more densely packed, so you have more collisions. So that increases the rate of reaction also. If the reactants are in different phases, for instance, if you have one of the reactants is a solid, then the only place that the reaction can occur is on the surface, right? It can't get into the center. The other reactants can't make it to the center. So if you divide it into smaller pieces, you get more surface area. And the surface area of the reactants then will cause the reaction to proceed faster. That's the problem in, well, for this region, in coal mines. If you get a buildup of coal dust, that has large surface area on a combustible material, the coal dust. And that's why all you need is a spark, and sets off that coal dust, and it reacts so fast, we classify it as an explosion. And then the last one is there a catalyst? What is a catalyst? A catalyst is any substance that is unchanged from before to after the reaction. It participates in the reaction, but it itself is not changed in the reaction. Okay, here's how temperature affects. And it has to do with the kinetic energy, the activation energy of the reactants. That's very simple. Causes, since they have a higher energy, higher kinetic energy, which temperature, if we haven't said this before, temperature is a measure of the average kinetic energy of all of the molecules in the substance. So if the temperature increases, the average kinetic energy of everything in the substance is increasing. And that increased kinetic energy accelerates the reaction by causing more of the molecules to possess enough energy to make the reaction go. They exceed the activation energy as a product of their increased kinetic energy. Okay, concentration effect. A higher concentration of reactants results in more collisions. And the more collisions you have, the more probability, the higher the probability of a reaction occurring. Their example here is a lit cigarette. At 21% oxygen, which is atmospheric, the cigarette burns at a pretty slow rate, actually. But if you light a cigarette in an oxygen atmosphere, say you're going to visit a grandma and she's in an oxygen tent, or she's got oxygen mask and she pulls it off for a second and the oxygen starts to fill the room. You light a cigarette and it just goes up in your face. The reaction rate is much faster because we've increased the concentration of oxygen. Oh, here's an example: phosphorus burning. Okay, we burn phosphorus, which is like lighting a match. On the right, we've got 21% oxygen, atmospheric, and on the left we have pure oxygen, which is a much more vigorous reaction. And it's based purely upon concentration of the reactants. Let's see, there are examples for increased surface area, weathering of rocks. Yeah, it occurs faster with more surface area. Explosions. I mentioned mine explosions from coal dust buildup, but you can have dust buildup, combustible dust buildup in other places, like grain elevators. They produce a lot of combustible dust. And they're required now to maintain air quality, just like coal mines are expected to do. They keep enough fresh air moving in and filter it out so that the coal dust doesn't build up. And in grain elevators, the grain elevators don't build up dust to a combustible level, which will accelerate the reaction. And the catalyst. You can increase the rate of reaction with a catalyst. And each catalyst works differently. Some catalysts are solid, like in your catalytic converter in your car. So you can have solid catalysts. You can have a solid catalyst. For example, in your catalytic converter, that solid is a ceramic bead or ceramic support covered in platinum and palladium. Those are the catalysts. The ceramic beads or the ceramic matrix is there just for support. Or you can have, let's see, liquid. In this case, aqueous potassium iodide. If you add that to hydrogen peroxide, then it will decompose explosively, very fast. Or you can have gaseous catalysts. And I can't think of one right now, but they do exist. The catalysts do participate in the reaction, and they participate in different ways depending on the catalyst. But the key is the catalyst goes in one side and comes out the other, supposedly unchanged. But on the microscopic level, it participates in the reaction. Now, what does a catalyst actually do in terms of activation energy? That's the key. The activation energy of the reaction with a catalyst is much lower than it is for the activation energy of the reaction without the catalyst. And that's what this diagram shows. This is the uncatalyzed energy here, activation energy, and this is the catalyzed activation energy. So how does that speed up a reaction? What it does is, since the activation energy is lower, at the same temperature, you've got more molecules, more reactants meeting the condition for activation energy when it's catalyzed than when it's not catalyzed, which speeds up the reaction. You've got more reactants that are able to transition to products if you have a catalyst. Let's see. Let's see. What they're doing here is they're making sulfuric acid, sulfur dioxide. They're making sulfur trioxide. Oh, they're catalyzing the reaction with nitrogen monoxide, NO. So NO combines with O to make NO2, and then NO2 combines with SO2 to make SO3, and then NO is reconstituted. So that makes it the catalyst. So NO over here comes out here as NO. The net reaction is exactly the same, but it occurs much faster. In fact, the key to catalysts is a catalyst provides an alternate pathway for the reaction. From the outside, it looks like that's the same reaction as it was before. But with the catalyst, it goes through a different pathway to get there, and a faster pathway. So I think that answered my question. Yes, sulfur dioxide is a gas. Nitrogen monoxide is a gas. So that's an example for the gas. Okay, here's the decomposition of hydrogen peroxide to make water and oxygen. It's usually pretty slow. So that bottle of hydrogen peroxide in your medicine cabinet will probably not decompose rapidly over time. If you increase the temperature, yeah, you may get your plastic bottle to swell as it produces gas. Or if it's old, it may have built up a lot of gas pressure. But if you combine a catalyst, in this case, they're using a manganese dioxide. But this is more common. Potassium iodide in solution will catalyze the reaction, and it will rapidly decompose, which means buildup of large pressure of oxygen. So one of my former students was married and expecting a child, and his wife had a ultrasound to determine the gender of the child, and they were going to have a gender reveal party. So what he did was he bought some hydrogen peroxide. It needs to be a higher concentration than medicine cabinet. The hydrogen peroxide in your cabinet for disinfection is 3% hydrogen peroxide, and he needed something more concentrated, 30%, which you can get on the internet. So he got that, and he got food coloring of the proper color, right? If it was a boy, it would be blue food coloring. If it was a girl, it would be red, which would turn out pink once it's mixed in the solution. And then for the gender reveal, nobody knew what it would be until he dumped his solution of potassium iodide into the bottle. Oh, and also he put a little dish soap in there, right, to make more foam, more bubbles. And it just squirted out the top in, I think it was a blue color, because the gender was male. Okay, here's your catalytic converter. Takes these incomplete combustants. Oxides of carbon and oxides of nitrogen are common as incomplete combustion products, and the catalytic converter completes the reaction to carbon dioxide and nitrogen. Now, the EPA and all the brainiacs in the world are trying to tell you that carbon dioxide is a pollutant. And in fact, it is not a pollutant. How do I know that? I know that because without carbon dioxide, green plants would die instantly. Green plants need carbon dioxide. It serves as food. They make construction materials and energy storage materials in their cells from carbon dioxide as the reactant. And they combine it with water and they make carbohydrates. So carbon dioxide is not a pollutant. Okay, so why do we stick enzymes in here, right? People have heard of enzymes and they have sort of a general idea of what enzymes are, but really an enzyme in its simplest form is a biological catalyst. Now that's an oversimplification actually, because while enzymes do speed up reactions, they do more than that. They actually control reactions. So the system in the cells that activates an enzyme can also deactivate the enzyme under certain conditions. And that allows it to control the reaction. So in this case, their example here, milk sugar, lactose, is broken down in reactions that are catalyzed by the enzyme lactase. If you as an individual do not have lactase that you produce in your upper GI to break down the lactose, then the lactose will go through your system into your lower gut, and down there, flora and fauna, microorganisms, bacteria usually, inhabiting your gut, produce their lactase. Lactase is the enzyme, and it breaks down lactose in your gut and produces gaseous discomfort. So those people who are lactose intolerant are cannot produce the lactase enzyme. So there are supplements. If you want to either drink regular milk, that's fine. If you want to drink lactose reduced milk, you can get that. But if you take this enzyme and mix it in your drink or take it as a pill, then when you drink the milk, it will break down in the upper GI and your body can absorb the sugar or absorb the products, excuse me. Okay, acids and bases. Right? We're still talking about reactions. Acids and bases, we have to define what an acid and a base is before we can talk about the reactions that they undergo. So, what's an acid and what's a base? Well, there's a historical foundation for this discussion. The acids and bases had been characterized through the Middle Ages, actually. And it wasn't until modern chemists needed to understand what they were before they could use them effectively in chemical reactions. Alchemists knew acids pretty well. In fact, they knew several strong mineral acids. They knew hydrochloric acid. They knew sulfuric acid. They knew nitric acid. And they knew what they could do. And before the modern age, acids had been characterized as being able to do certain things. Well, this chemist, Svante Arrhenius, who was Swedish, his explanation for the character, what caused, now, what was the chemical structure of an acid or a base? Arrhenius said that all acids started with a hydrogen, and they were attached to something else. So that when you put them in aqueous solution, that hydrogen would dissociate. Right? So if this is neutral, then you have to have an equal positive and negative charge on this side. And that hydrogen is responsible for acid character. He said bases were molecules that contain OH groups. And you'll know from previous discussions, I think in chapters maybe 11, the bases possess a hydroxyl group, OH. And when you put these in aqueous solution, they dissociate into those two components. Okay. And for most acids and bases, that's true. There are some exceptions. And I'm not sure if we're going to get into those in this class. That might be a little deeper than we want to go. Oh, they do make mention. Okay. But I'm not sure if no, I don't think they do that. Okay. So Arrhenius' definition works for most acids and bases. And notice, we also know the physical characteristics of acids and bases. Acids taste sour. Okay? Bases taste bitter. Yeah, taste bitter. Now you can't do that with some acids and bases because they would eat your tongue off. But as a general rule, if they're weak, for example, vinegar. Vinegar is a solution of acetic acid. A 5% solution of acetic acid will give you vinegar. And if you combine an acid and a base, they neutralize one another. In other words, in the right proportions, you no longer get acid or base character. So we attribute that to this reaction, right? Hydrogen from an acid, hydroxyl from a base gives you what? Water, right? 2 hydrogens and 1 oxygen gives you water. Okay, so these are some other properties of acids. When you dissolve acid in water, the solution will conduct electricity. We can test them with indicators. A strip of litmus paper, which has been impregnated with the litmus dye, will turn from blue to red if exposed to acid in water. I mentioned the sour taste. And with the ability to neutralize bases, that's what we've done here. Combine an acid and a base, that's called a neutralization reaction. And with some metals, acids will react with the metals and liberate hydrogen gas. Not all metals, but some. Whereas a base also conducts electricity. Now, why is that? Acids and bases conduct electricity. They have these mobile ions, right? Anytime you've got mobile ions in whatever form it takes, you can conduct electricity across that substance. So bases will conduct electricity. The litmus test will go from red to blue. So blue represents base, red represents acid with the litmus dye. And the reaction to neutralizing acid is there also. Another thing that's not mentioned here is if you put a base between your fingers, it feels slippery. Now, the conventional wisdom is that what happens is the base converts the oils in your skin, on the surface of your skin, into soap, and that makes it feel slippery. And that reaction, I'm not sure if we're going to get to that one here or not. So just store that away in the back of your brain. Okay. Now, HCl is normally a gas. Hydrogen chloride is a gas. But when you dissolve it in water, you get hydrochloric acid. And the reason it's an acid is because it will dissociate. It dissociates into hydrogen ions and chloride ions. And the hydrogen ions give it the acid character. Now, this is also known as a strong acid. And in chemical terms, strong means complete dissociation. So HCl, when it goes into solution, breaks up completely. There are no HCl molecules left. It's all hydrogen and all chloride. That's strong. Now, if the concentration is very low, it's still a strong acid in chemical terms. Okay. Okay, so what actually happens? Well, we'll use hydrochloric acid as our example. In aqueous solution, water doesn't just sit there. Water is a participant in the reaction. It is a reactant. So when we put HCl in solution, it reacts with water. And notice that this hydrogen ion, we can write the reaction as a dissociation, hydrogen and chloride. But hydrogen ions never exist free floating in any solution, aqueous solution. They always combine with water. So they might be transferred from this. They'll transfer to water and produce that ion, the hydronium ion. Okay. Sometimes we write the dissociation of hydrogen chloride in aqueous solution, simplified version, as producing hydrogen ions and chloride ions. That's for convenience. Physically speaking, that's not what happens. I should say chemically speaking, that's not what happens. But for convenience and for calculations, it's perfectly acceptable to do it that way. So this is a representation of what happens. That hydrogen is transferred to this molecule of water, and now we've got 3 hydrogens, right? But it's got a positive charge because the hydrogen had a positive charge when it combined. And the negative charge is retained by the chlorine. Okay, I stole my thunder earlier. Strong acids like hydrochloric acid, nitric acid, sulfuric acid, they completely dissociate in aqueous solution. Whereas weak acids only partially dissociate. So acetic acid is this one. H here and the acetate polyatomic ion there. So if we write this in terms of an equilibrium, we can say HC2H3O2 plus water yields hydronium plus C2H3O2 minus. That would be a true reaction in one direction. But for weak acids, we can represent it this way, with a tiny arrow that way and a big arrow that way, which means it's mostly in that form and only slightly in that form. That's a weak acid. Okay. If we test the acids of equal concentration, we put a certain amount of HCl in solution and the same amount by mass in aqueous solution of acetic acid, and try to run an electric current through them and show that with a light bulb, the strong acid will make a very bright light and the weak acid will make a very weak light. Because the weak acid doesn't have as many ions in solution to transfer the charge, to make the current go in the circuit. Okay, that looks like it's kind of out of whack there. But this is the same what I've drawn here. That's what you're seeing right there. What we're describing here is a dynamic equilibrium. Remember, dynamic, it comes from the Greek word for power. So dynamic means there's action going on in there. The equilibrium part is from the outside, you measure concentrations of these two and this one, they seem to not change, right? They just stay the same. But on the molecular level, down where the atoms are active, this forward and reverse reaction is occurring at a furious pace, forward and reverse. what happens is when you reach that equilibrium point, the rate of the forward reaction equals the rate of the reverse reaction. So it may be happening, but the rates balance each other out. Okay. Acids are extremely useful, right? Sulfuric acid has a number of industrial purposes. You'll see it used in the steel production. It's used to pickle. They say it's to pickle the iron, and it cleans the surface of the iron of any rust or any contaminants. Actually, sulfuric acid is used in the paper production. So it causes the decomposition and the separation of fibers in wood, so that they can get the fibers apart and make product out of it, paper, what have you. And during that reaction process, the sulfuric acid converts to products of sulfur dioxide. And that's why when you get close to a paper mill, you will smell sulfur. Let's see. Fertilizers. Yep. Fertilizers are, phosphate fertilizers are heavily dependent. The industry for producing good phosphate fertilizers is intimately connected to the use of sulfuric acid. We use hydrochloric acid in our stomachs, right? It's not so concentrated that it'll eat a hole in your stomach normally, right? If it does start to do that, then that produces ulcers. But, or gastric upset. But it's just concentrated enough to start the digestive process. Citric acid in citrus fruits, right, to give them that sour flavor. Carbonic acid and phosphoric acid both are contained in soft drinks. The carbonic acid is what produces the fizz, and the phosphoric acid is there for flavor and for maintaining the other components in the mixture. Acetic acid, of course, is vinegar. Okay, how about the Arrhenius base, right? In this case, we've got the hydroxide polyatomic ion attached to sodium. So sodium hydroxide is a base, and it's a strong base because in aqueous solution, it completely dissociates into sodium ions and hydroxide ions. Now here's a difficult concept. Ammonia, when we dissolve it in water, produces a basic solution, but the molecule itself does not contain hydroxide. So what's going on here? What happens is, just like acid reacting with water, ammonia reacts with water. And when it does, the ammonia takes a proton from water, a hydrogen ion from water. So we get ammonia converted to the ammonium ion. And what's left? Well, we have to balance charges, so we need OH minus over here. And it's missing the minus sign. But that's what makes it a base. In aqueous solution, ammonia produces a basic solution because there's your hydroxyl. But it doesn't fit the theory of Svante Arrhenius, in that the molecule does not contain hydroxide on its own. It only produces hydroxide when it's dissolved in water. Okay, and for this course, we can't go into any more details. There's another theory that deals with that. on the acid base side. And if you run across it in the future, I'll just tell you, it's it goes by the name Bronsted-Lowry, right? But you won't have to know it for this course. It's just a bit of information in case you're confronted with acid-base theories in the future. Okay. So there's a curious behavior of water. Pure water will auto-ionize. In other words, one water molecule encounters another water molecule, and one molecule transfers a hydrogen to the other one. So when it does that, it produces a hydronium ion and a hydroxyl ion. Right? Now it doesn't do a lot of that, right? That's why these arrows are different sizes, right? There's only a very small amount that actually produces this reaction. Most of it remains as water, H2O. But this reaction goes on all the time in any aqueous solution. It's one of the reactions that occurs, in addition to any of the others that may occur. And in pure water, this is the only reaction that can occur. Okay, so when that happens, we produce equal amounts of hydronium and hydroxyls, right? So because they're equal amounts, then there's no winner, right? You don't have acid or base in excess in pure water. So that's what's called neutral. Okay. It's only when we add extra of one or the other, either hydrogen ions in the form of hydronium or hydroxyls, that you get an imbalance and you produce either an acidic solution or a basic solution. It's the balance. Now, the one way that we conveniently express the acidity in a quantitative way, or basicity in a quantitative way, is with the concept of pH. Okay, in order to understand pH, we need, let me flip to the next slide and see if I don't steal thunder. All right, I'm going to show you how pH is calculated. So when we get this reaction of water and water, like that, and we produce this and this, what we produce on this side is, let's see, have we introduced the concept of, hold on a second, let me look it up. I don't want to use words that we haven't defined yet. Hold on. Okay, we haven't got there yet. All right. Maybe now is a good time to do it. I'm going to introduce the concept of concentration. Shoot. I really ought to go to the back end. Hold on a second. Yeah, in order to, the authors have put these things in the wrong order. So I'm going to flip to the end of this slide set so that we can talk about this more intelligently. But first we'll have to define terms. All right, so bear with me. And I'm going to go back here to concept of the mole. Okay. Avogadro's number. It's not anything mysterious. Avogadro's number, or the mole, is simply an expression of numbers of things. How many do we have? And the reason that the mole was developed as a unit of measure was that on the atomic level, if you've got just a little bit of something, you got lots of atoms, a huge amount. So we invented this unit of measure to make it more convenient to discuss these large numbers, and that's the mole. And the mole is actually 6.02. That's not the one I used. 6.022 times 10 to the 23rd is the mole. And it could be anything. For our purposes, it's atoms and molecules. But the mole could be, I don't know, 10 to the 23rd chickens for all I care. That's a mole of chickens. So Avogadro didn't invent this number, but his theoretical concept, his concepts that he developed were instrumental in determining the value of the mole. So his name was assigned to it as an honorarium, so to speak. All right, so we have to define what's a mole, and we know that if we have exactly 12 grams of the carbon isotope, C12, and I know we've discussed isotopes before in previous chapters. If we have 12 grams of that isotope, we have exactly 1 mole of carbon-12 atoms. So that's the anchor, that's the fixed amount. And from there, we can compare the rest of everything to that. So when we look at the periodic table and we see a value for, let's see, oh, I don't know, 15.9994. grams of oxygen. If we have that many grams of oxygen atoms, we have 1 mole. Okay. Now we have an equivalence. This many grams per mole, which is a conversion factor. This is the atomic weight of oxygen, roughly 16. Okay, so now that we know what a mole is and what we mean by molar mass, right? That's what I used earlier. Atomic weight is molar mass. The molar mass of atoms is if you have that many grams from the periodic table, if you have that many grams of an element, you have 1 mole. Right? So you can do this calculation for molecules too. So if you have, and we can round this off to 16 grams per mole. If you have 2 hydrogens and 1 oxygen, you would add 16 for the oxygen, and hydrogen is 1.01. You got 2 of them, right? So we have 18.02 grams per mole of water. Okay, that's the molar mass of water. Okay, so we have different examples here. Copper is 63.5 grams per mole. All right. So concentration, let's see. All right, so let's go back to acids and bases. There we go. Okay, so now that we know what a mole is, we can express concentration in terms of how many moles of something per unit volume. And the unit I want to use here is called molarity. We abbreviate with a big M. Molarity is equal to the number of moles, and that I use a small n without the zero. Little zero up here would be neutrons. This is moles per liter. So the liter of solution would have so many moles of, in this case, hydrogen ions or hydronium ions. And that would be so many molar. So 1 molar solution would have 1 mole per liter. Okay. Now that we know that concentration unit, this reaction produces, for pure water, produces 10 to the minus 7th molar. A really small amount, right? So we weren't kidding with that small arrow going this way. It only produces 10 to the minus 7th molar concentration of hydronium ions. And since they came from the same place, we also produce 10 to the minus 7th molar hydroxide ions. And since they're equal, the solution is neutral. If they're out of balance in any way, then if we increase one, then the other has to decrease. And I can't really show you how that is right now because it's beyond our discussion. But I wanted to give you this much to lead into the pH scale. We can calculate the concentration in any reaction of hydrogen ions and hydroxyl ions. But expressing them even in scientific notation can be unwieldy. So what happened was, let's see, Sorensen. Do they mention Sorensen in here? Sorensen. They don't get to him right away. He was a Swedish guy. Sorensen wanted to work with something a little easier to manage. So he invented this mathematical transformation of the hydrogen ion concentration of a solution so that it could handle it better. So what he said was, let's use a logarithmic scale, right? If we take the common log of that number, of the molar concentration of hydrogen ions, what do you get? Well, remember the rules of logs. This is base 10, right? And then when you take the log of a number, you're saying that the log of the number is the power of 10 that represents this number. So basically, if it's base 10, then the log of that number is the power of the 10. So that would be minus 7. Okay. But Sorensen didn't want to deal with negative numbers either. So he said, all right, we're going to get rid of the negative. Put a negative here, which means a positive 7. So this is a neutral solution. pH neutrality is always pH 7. It's little p, big H. And you can do this for any concentration. It doesn't have to be only the power of 10. I mean, it can be anything. It can be 2.45 times 10 to the minus 4. Negative log of that will be something, right? That's where you need your calculator. It's just a mathematical transformation. Okay, so that's why neutrality is 7. And acidity is smaller numbers. Right? Let me prove it to you. What would be the concentration that's greater than 10 to the minus 7th? 10 to the minus 6th? 10 to the minus 5th would be a bigger number, wouldn't it? So if we did 10 to the minus 5th, a pH 5 is more acidic. So the smaller the number, the more acidic. Right? And the bigger the number, the more basic. And notice, because this is a logarithmic scale, when you go from one unit to a smaller unit acid, you're actually increasing concentration of hydrogen ions or hydronium ions by a factor of 10. It's a logarithmic scale. So pH 5 is 100 times more concentrated in hydrogen ions than pH 7. All right. That's the pH scale. And for example, we can measure the pH of normal blood. A person who's not in distress in any way, the pH of their blood will be between 7.35 and 7.45. It's a very narrow range. Anything outside that range puts you in jeopardy of health consequences. Okay. All right, this is talk about neutralization of acids, bases, acid-base reactions. Okay, let me see. Let me go to the next slide and see. No. Okay, as far as chemistry is concerned, when you get an acid and a base reacting, let's use hydrochloric acid in aqueous solution and sodium hydroxide in aqueous solution. What are they going to do? They're going to neutralize one another. The hydrogen ions and the hydroxyl ions will produce water. So what's left over? Chlorides and sodium. Sodium and chloride. That's a pure liquid, and this is in aqueous solution. Okay, so in chemical terms, what you've got is an acid reacting with a base produces water and a salt. In chemical terms, this could be anything. It doesn't have to be sodium chloride. It doesn't have to be table salt. Right? If this was a different acid and a different base, it would produce a different salt. But in chemical terms, it's still a salt. And these are examples here at the bottom. Potassium hydroxide in hydrochloric acid produces potassium chloride. Or calcium hydroxide in phosphoric acid produces calcium phosphate. All right? Okay. I'm not sure why this one is in here. It has to do with, and I mentioned this in a previous video, how to write waters of hydration for compounds. We use this dot in the middle of the line, and then how many waters are attached to each molecule of the compound. Right? When you have water attached to copper sulfate, it turns blue. When we heat it up and drive off all the water, we have copper sulfate with no water. That turns white. And then if you add water back to it, you reconstitute the hydrated compound. Okay, White Sand National Monument in New Mexico. This sand is produced from gypsum, calcium sulfate dihydrate is gypsum. That's why it's so white. It's like wallboard, right? Wallboard in the walls of your house is made from gypsum. These are different examples of acid-base reactions. And in this case, we've got hydrochloric acid and magnesium hydroxide. Produces water. What's the salt? Well, magnesium and chlorine. Magnesium chloride is the salt. And this is the balanced equation. We know that we've written the compounds correctly because the charge is balanced. Chloride is always -1. Magnesium is always 2+. So we need 2 chlorines, which are minus each, to balance the magnesium. That's why MgCl2 is the correct formula. Similarly, for aluminum hydroxide and hydrochloric acid, do the same reasoning to get there. Acid, okay, I see what they're getting at. Say you have too much hydrochloric acid in your stomach. You got a sour stomach. Eat a Tums. Tums is composed of ground up limestone, right? Pure limestone is calcium carbonate. So they just grind it up, make sure it's not hazardous, you know, it doesn't have any contamination, bacterial contamination. They grind it up and they press it into tablets and sell it as Tums. And they put flavorings in it, so forth. And what it does is the calcium carbonate reacts with the acid in your stomach and produces as a product carbon dioxide, water, and calcium chloride, salt. Here we go. So here's the reaction. Hydrochloric acid in your stomach, calcium carbonate produces carbon dioxide, water, and calcium chloride. And if you've got a really, really bad sour stomach, when you eat your Tums, it may make you burp because you're producing this carbon dioxide gas. And there's evidence of the gas production. Okay, let's see. You can do this with other carbonates. Sodium carbonate, which is, let's see. I forget the common name for it. But it produces the same product. Carbon dioxide, water, and salt, just a different salt. Okay, other types of reactions. We talked about synthesis, decomposition. We talked about single replacement reactions. Now, double replacement reactions are possible, and actually we've been using double replacement reactions up till now. What happens is, when you get these two compounds in the vicinity for reaction, they just swap partners. So A goes with D and B goes with C. That's a double replacement reaction. And here's an example. Potassium chloride and silver nitrate. When you put those two together, you get potassium nitrate and silver chloride. They just swap partners. The key to this reaction, though, is that potassium chloride is aqueous. It's in solution. Silver nitrate is aqueous in solution. And whenever the ionic compounds go into solution, they produce independent ions. So potassium ion, chloride ion, silver ion, nitrate ion are all floating around in that solution. That's aqueous. That's aqueous. This is aqueous. And this is, excuse me, this is aqueous. So what happens? Well, this cation combines with this anion to produce, but as it turns out, silver chloride is not soluble in water. It produces a solid. So when you add these two together, they might be clear as independent solutions, but when you put them together, they get cloudy because this solid is dropping out of solution. It's called precipitation. But the potassium and the nitrate, when they react, they are independent still in solution. They actually do not react. Okay, so the driver for this reaction is the production of that solid. It forces the reaction to go this way, that precipitation. Okay, right, this is a precipitation. Double replacement precipitation reaction. A precipitation reaction is a subcategory of double replacement. Precipitations occur in aqueous solution. Here's another one. In this case, potassium iodide and lead nitrate, lead 2 nitrate, if we write it correctly, produces potassium nitrate and lead 2 iodide. As it turns out, though, lead 2 iodide is insoluble. So it produces this yellow color. That's lead 2 iodide. And what I'm saying is, this is written lead 2 iodide. That's because this is a -1 and you got 2 of them. So that makes this one a +2. Okay. So that +2 is designated here in the name. Okay, what do we have here? Sodium sulfate and barium chloride. All right, barium sulfate is insoluble. It precipitates. So you got the similar type of reaction here. You just have to determine which one is insoluble. Now, if the potential products are both soluble, then you really don't have a reaction, right? Because they're all independent ions floating around in solution and they're not doing anything. So technically you don't have a reaction if everything is still soluble. It's only when you produce a precipitate that you get a reaction. Okay, that's a double replacement reaction with precipitation. This reaction we're discussing now is called oxidation reduction, or abbreviated redox. Okay, oxidation reduction is redox reaction. And we don't say oxred reaction because it just doesn't sound right. So redox reactions are oxidation reduction. Now, this is an oversimplified definition. It's true but it really doesn't speak to the proper definition for oxidation. And I've got a little mnemonic device to tell you what oxidation reduction is. It's called oil rig. Oxidation is loss. Reduction is gain. Loss of what? Gain of what? Loss of electrons. Gain of electrons. So in every oxidation reduction reaction, electrons are transferred. Oh, they do tell us that there. Just put it in small print. Actually, the small print should be large print and the large print should be small print, because truly oxidation is loss of electrons. And these two processes always occur together. If electrons are lost from someplace, they got to go someplace and they're gained somewhere else. So oxidation and reduction always occur together. Here's an example. Let's see, hematite, Fe2O3, when it's combined with carbon or coke in a blast furnace, it produces iron, pure iron, carbon and carbon dioxide. Okay, so what's happening? Well, do we know that this is an oxidation reduction reaction? Well, let's write it out. Fe2O3 yields Fe and 3CO2. Oh, I left out the carbon. Excuse me. How many of these we got? 2 of them. Okay. Plus carbon, which is 3. Okay. And then we have 4 irons. There we go. Now it's balanced. So how do we know that electrons were transferred? Well, really, I can't discuss this in detail unless I use another accounting technique. It's called oxidation state. So the oxidation state is a way of accounting for electrons. For neutral elements like this iron, the oxidation state is 0. You can equate that to a charge. It has no charge. This one has no charge. But in this compound, the oxidation state of carbon has changed, right? Oxygen is always taken as -2. Yeah, unless it's a peroxide. But for most purposes, oxygen is -2, oxidation state. So 2 times -2 is -4. So that means in order to balance the oxidation states, carbon must be a +4 oxidation state. Okay, so it's gone from 0 to +4. How do you do that? If you go from 0 to +4, you've lost 4 electrons for each carbon atom. Right? Lost 4 electrons per carbon. Okay. How about the iron? Well, the iron's 0 here. What is it over here? Well, remember, oxygen is -2, so that's -6 total. So we need a +6 here to balance it. But we've got 2 of them. So this iron should be +3. So if we go from +3 to 0, we had to gain 3 electrons per iron. Okay? That's how you get from a +3 to a 0. You add 3 negatives and they balance out. But Another characteristic of oxidation reduction reactions is the number of electrons transferred in the oxidation step must equal the number transferred in the reduction step. So if we've got 4 electrons here, per carbon, we actually have 3 times 3 equals 12 electrons transferred. And this is 3 electrons times 2 times 2 is 4 times 4 ions equals 12 electrons. Okay, so we have the same number of electrons transferred from oxidation and from reduction. All right. So we say that the hematite has been reduced because we added electrons. Remember, oil rig, reduction is gain. So the hematite was reduced and the carbon, the coke, was oxidized. And this happens at extremely high temperature. Okay. So you just got a crash course in redox reactions. In my chemistry course, we do this all in one chapter and get 1 exam on it. But since this is an abbreviated course and physical science covers a lot of ground, you get a crash course in it. Now there's the concept of activity. Activity refers to how active are metals. When we compare 2 metals, we can say one is more active than the other. And the way we do that is if one of the metals is combined, is in a compound as an ion, then the question is, can the free metal that's opposing it, can it replace it in that compound? If it can, then we say that the replacing metal is more active than the ion in the compound, the metal in the compound. That's what activity means. And this occurs in the solution. And we can order these things right here. Now, this activity series is based upon reduction potentials. And I won't elaborate on it, but what it means is that we can quantify the activity of these metals relative to one another and actually produce electrochemical cells or batteries based upon that evidence and calculate the voltage of that cell. But we don't have time or the requirement to do that in here. So we're going to discuss them in terms of activity only. So what we're saying is that anything, if you're comparing 2 metals, say lithium here and aluminum, lithium is the more active metal. So that means if aluminum is in a compound, lithium will replace it and release the aluminum. Let's see, we have an example. Zinc and copper. And these are characterized by single replacement reaction. That's what this activity series is based upon. So, for example, if we have zinc and copper sulfate, so we have zinc metal and copper sulfate in aqueous solution. The question is zinc more active than copper? Well, if we go back to the chart, let's see, zinc metal is here and copper is down here. Zinc is more active than copper. Notice, because zinc is up here, copper's down there. So when we write this, zinc should replace copper. And it will produce in the process copper metal plus zinc sulfate. And as it turns out, that's a balanced equation as written. And this happens only because zinc is more active than copper. If we put these two together, you won't get a reaction because copper is not active enough to replace zinc. Okay, this is an artist's idea of what's happening. And in the process, we can also say that this is an oxidation reduction reaction. How do I know that? Well, there's a rule of thumb. If you have a free element on one side, and that element is in a compound on the other side, you have an oxidation reduction reaction. You don't have to do any calculation. You know it. Metal compound, or metal or element compound, element compound. You have an oxidation reduction reaction. And we know in this case that since this is zero oxidation state, and over here it's 2 plus, how did it get there? It had to lose 2 electrons. Right? It lost 2 electrons to go from a 0 to a +2. Where did those electrons go? They went over here. And they reduced copper. Reduced the copper ion to copper metal, and the zinc metal was oxidized to zinc ions. Okay. So this is a strip of zinc, and this is copper sulfate. Remember, copper sulfate's blue because it's combined with water. And then over time, we get that zinc replacing the copper in producing zinc sulfate in solution. And zinc sulfate is clear. It's no color. But we do get down here copper metal. Okay, so that's proof that the reaction has occurred. Okay, let's see. Now they're saying reacting copper metal with a solution of silver nitrate. So if we put copper in here, right here, and silver nitrate, will we get a reaction? That's the question. Well, we have to look at the activity series. Let's see, let me back up. Here we go. Copper and silver. So let's find silver. Silver is way down here. Copper is above it. So copper will replace silver in that compound. And we'll get silver metal and copper nitrate. Let's see. Copper, well, it could be. Let me see. I need some help with this one. Yeah. Okay. So this one is +1. This one's 0, -1, 0, +2. So that means this one has to be 2 because the nitrate polyatomic ion is -1 charge. And then to balance it, we need 2 nitrates, which means we need 2 silvers. And now we're balanced. Okay. So we can tell which one lost electrons. Copper went from 0 to 2 plus, lost 2 electrons per copper. And then silver gained an electron for each silver. But there are 2 of them. So there are 2 electrons transferred actually, which balances the 2 electrons for the other. And this is what it would look like. right? See the silver replacing the copper here? Well, the copper replaced the silver. Now the silver metal, and then the copper nitrate is a blue color. Okay, let's see. How about aluminum metal in a solution of copper sulfate? Will we get a replacement? All right, so let's look at the activity series. Let's see, what was that? Aluminum metal and copper sulfate. So where's aluminum? Aluminum is right here, and it's more active than copper. We will get a reaction. Aluminum will replace the copper, produce aluminum sulfate, and aluminum has lost electrons to go from 0 oxidation state to 3+, and copper has been reduced by gaining electrons from 2+ charge to, or 2+ oxidation state to 0. Okay. How about metals and acids? Aha. So now, instead of replacing another metal, we're thinking about hydrogen. And remember, let's look at that activity series. Here's hydrogen in capital letters just to make it stand out. But any metal above hydrogen here will replace it in an acid. Okay. And in the process, it will produce hydrogen gas. So here we have iron and sulfuric acid. So iron is, let's see, where's iron? Okay, iron. It's above hydrogen, so we will get a reaction. And the gas that's produced is hydrogen gas. So what would be a qualitative test for that hydrogen gas? Well, all you have to do is collect it in a submerged and inverted tube, fill the tube with water, and then plug it with your thumb and submerge it. Of course, you have gloves on. And then catch the gas as it goes, and it fills up that tube, and then pull the tube out once it's full, and then take a glowing ember and stick it in the tube, and it should pop, because you're getting hydrogen gas, oxygen from the air combining, and the reaction is very fast. It makes a sound. Let's see. Okay. Reactions with water. Well, let's see. Metals above magnesium in the activity series will undergo vigorous replacement reaction with liquid water. So they have to be above magnesium in the activity series to react with water. See, water technically could be considered a very weak acid. Let me see, magnesium, hold on a second. So only metals that are above magnesium, sodium, calcium, potassium, lithium, those are all alkali metals. They're in the first group. Those are the only ones that will react with water to produce hydrogen. So let's go back. Here we go. Here we go. Oh, wait a minute. Calcium? Metals above magnesium in the activity series. Oh, I'm sorry. They're not, excuse me. They're not all alkali metals. Calcium is an alkaline earth, but it's more active than magnesium. Okay, so sodium, potassium, lithium, and calcium will react with water, but the rest of these will not. At least not in that reaction to produce, hydrogen gas and the base, calcium hydroxide. So this is what it looks like. Right? Magnesium will not react with water, whereas calcium will. Okay, this is a summary of the types of reactions we've looked at so far. Combination or synthesis reactions, decomposition are flip sides, same coin. Combustion reaction, single replacements, where you have two metals or where you have a metal and an acid. We just looked at those. Double replacement where you have precipitation. Double replacement where you have an acid, a base, produces water and a salt, right? That's a double replacement. And acid carbonate produces water, carbon dioxide, and a salt. All right. This is just a pretty picture with different types of reactions, so we don't need to dwell on that one. Besides, it's getting late. We've already talked about Avogadro's number and the mole, so we don't need to discuss this again. Let's see, and that's it. That's it for chapter 13. Stop the share, and we're done. Chapter 13. Next chapter is 14, organic chemistry. Let's see, just take a peek. Yeah, organic chemistry. All right. So when we get to chapter 14, we're going to talk about organic chemistry, and I'm going to cover organic chemistry in one lecture, whereas if you were taking my series of organic courses, which is 2, it would take us 2 semesters, 2 terms to do it. So you're going to get a real shotgun blast of organic chemistry in a very short period of time. Try to give you some of the basics. We're done.